Okay, welcome everyone to this continuation of what are my favorite theorems. Very biased collection in case it wasn't clear. Very biased, favorite theorems as usual. One of my favorite sequences, very biased, my favorite sequence, the so-called Cantor sequence. Cantor sequence, a Cantor set sequence, I can't decide. But we'll see what it is. It starts off like this, and I'll let you guess what the next value is. So it starts off by 1, 0, 1, 0, 0, 0, 1, 0, 1. And if you're guessing now the next entry is 2, then you're wrong. Anyway, we'll see what it is. I shouldn't let you guess what it is, actually. It's related to the Cantor set. Cantor set, I don't know. I just know this Wikipedia has a really beautiful article about it. Where it's on the Wikipedia article for the Cantor set, that it actually doesn't go back to Cantor. As usual, everything goes back to someone else. We're all standing on the shoulders of giants, and everything is misnamed anyway. So it actually goes back, apparently, to this old Egyptian pillar, where you can kind of see the Cantor set coming up here, and it kind of splits like whatever. If you go to the Wikipedia page, you can zoom into the picture. It's probably a little bit nicer. But anyway, let's talk about the mathematical Cantor set. And essentially it's the following idea. You have a line, you remove the middle third. This is a bad color, so maybe I use this one. Remove the middle third, so you get two distinct lines, and now you repeat the process. You remove the middle third of each one of them, and you get more and more of those little beasts, and you just keep on going until you can't draw them anymore because they are too small. And this is really the prototypical example of a fractal, although it wasn't explained. It wasn't introduced as a fractal because the idea of fractals came later. It's still a prototypical example, and the fractal dimension, the amount of self-similarity, the amount of how much space it fills, if you want, is this number log2 3. Right? So you remove every middle piece, so you don't have log3, which would be 1, dimension 1, like for the line itself. But since you remove the middle piece, you get log2 3, which is roughly 63%. So it fills like 63% of the space a line would fill. Okay, Cantor sequence, excellent, wonderful, everyone. Sorry, Cantor set, not yet sequence. Cantor set, excellent, everyone loves it. I hope you love the Cantor set. If not, I'm very, very sorry for you. Anyway, so make it discrete, because I don't like analysis. Analysis doesn't like me. I don't know. Both maybe neither. I can't tell. But anyway, discrete is usually much nicer and much more beautiful and much more adaptable to the human brain. So I make a nice type of sequence, which is called the Cantor sequence. And it works as follows. It really just now stretches out the Cantor set. You kind of can see this here in this plot. It stretches out the Cantor set over the natural numbers now. The Cantor set is just this line segment. Now I stretch it over the natural numbers. And I do it as follows. I define the Cantor sequence to be 1 whenever the next one, the ternary, the 3 with base 3, expansion of n contains no 1. Okay? Then I get a 1. So this is where and otherwise I write a 0. This is where my sequence here starts. So 1, 0, 1, right? It contains no 1, then I write a 1. It's a little bit confusing. It contains no 1, then I write a 1. So it starts with 0. 0 contains no 1, so I write a 1. Then it goes 1. 1 contains a 1, so I write a 0. Then it goes 2. Well, 2 contains no 1, and so on. Right? Okay. If the ternary expansion of n contains no 1. Okay. Very simple definition actually. And this is the sequence, and it goes like whatever. 1, 0, 1, 0, 0, 0, 1, 0, 1, and whatever. And it stretches out like the Cantor set, so there will be long stretches where you have a lot of zeros, because there will be 1s in the ternary expansion. And this is really just the Cantor set stretched over all of the natural numbers. Another very nice function. And you wonder about the properties and the behavior of that function. It should kind of mimic the Cantor set, in a function sequence in a sequence form. And what you can do is, whenever you see this picture here, like everything goes up and down like hell, what you can do is you just take, for example, what is the average value of the Cantor sum? That's what you could ask, right? So you just take the sum over all of them, and taking the average would then be divided by n. But let's say we want to study the behavior of the sum over all elements of the Cantor function, the Cantor sequence. So we sum them up, and it goes like this. So because there's these long stretches of zeros, there will be long stretches of no movement at all, and then it kind of goes up a little bit, and then doesn't move, and then it goes up a little bit, doesn't move, it goes up a little bit, doesn't move, and so on. But eventually it kind of goes off to infinity. That's what it seems, and you can be very precise. So the growth rate, which goes off to infinity, is essentially, so remember that this little thing here was our log 2, 3, which was the dimension of the Cantor set. So the growth rate in which this goes to infinity is essentially the dimension of the Cantor set itself, which is kind of a very cool statement. In particular, if you take the average, so if you divide this number by n, you get some n to the minus something, yeah, because we just subtract 1 from the exponent, and then the average will go to 0. As kind of expected. There will be lots of zeros. It's very similar behavior to the Cantor set. It kind of vanishes, it kind of dust. It vanishes, you can't see it anymore. And here, the average goes to 0, so essentially every entry is 0 in the end. Yeah, and that's a theorem, by the way. So the Cantor sequence behaves like, why is it a minus? It's clearly not a minus. Cantor set behaves like n to the log 2, 3, which is like this entry here that we have seen here. And there is some function in front, some bounded function. So you can kind of see it here. So scalar 1, scalar 0.6. I don't know, by the way, I don't know what the lower scalar is. I just guessed 0.6. So there's some scalar that you can put upstairs and you could put downstairs. There will be some bounded function that controls how it moves. And this growth rate is a dimension of the Cantor set, and the function itself, the h actually, this thing, so you can kind of see here, so you just need to divide now the sum by its growth rate, and you get this crazy behavior, which is really just Cantor's staircase, the devil's staircase function, the Cantor function just now kind of stretched over all of the integers, kind of fun. So it goes up and then slides down again, and goes up and it slides down all the time, essentially. Because these little gaps, you see them everywhere. It's kind of a fractal function. So if you would zoom in, you would see them nicely turning up. And why do I like this function so much is because it appears naturally if you study representations of SL2. So very early on in your study, you learn about groups. But this group turns out very late, but it turns out to be one of the most important groups ever. SL2, everyone likes SL2. It's kind of interesting enough to kind of force people to do research on it, but it's still easy enough that you are able to do research on it, right? So some groups are just too simple, boring, nobody researches on them. Some groups are just too complicated, yeah, nobody can research on them, and SL2 is somewhat in between. So SL2 really just 2x2 matrices with determinant 1 with whatever kind of entries you want. And people wrote whole books about that. The two most famous one, or certainly the most famous one, is the original book by Serge Lang, which is with a fantastic title, SL2R. So R is the real numbers. That's the title of the book, just SL2R. So I write a book about SL2R, but you will find other books. So here, SL2FP, FQ, for example. Yeah, so people are very fascinated by this group, and I'm also really fascinated by it. It's kind of extremely fascinating what you can pull out of this group. You can pull out the Cantor set from this group, for example, because the Cantor sequence, which is essentially equivalent to the Cantor set, as soon as you know the Cantor sequence, as I just explained, you get devil's staircase, the Cantor function, you get the dimension of the Cantor set. You essentially already have the Cantor set here. You just need to squeeze it now to an interval. So the definition of the Cantor set is the definition of the Cantor set implies the definition of the Cantor sequence, and vice versa, essentially equivalent. But you get this sequence as a weight space of dimensions of representations of SL2, which is kind of really exciting. So you can just rediscover Cantor's function, XYZ, set, sequence, whatever you want, from SL2, which is kind of really, really fascinating. So there's this one group, SL2, which generates a lot of interesting data. And this is just one of the examples, which I haven't seen anywhere, actually. So that SL2 can generate the Cantor set. Anyway, I hope you like the Cantor set. I hope you like SL2. I hope you enjoyed this video. And I also hope to see you next time.